Hello everyone. So far we talked about events, which are subsets of the sample space. Now we introduce random variables. These let us do calculus with probability. A random variable x is a function that takes an outcome and turns it into a number. For example, roll 2 dice and let x equal the sum of the numbers that these dice show. X can be 2 through 12, 2, 3, 4, 5 through 12. Also, for another example, measure server response time can be also a random variable. X is the time in milliseconds. In this case, X is a random variable showing the time in milliseconds. We have two kinds of random variables. There are two main types of random variables: discrete random variables, which take countable values. They can be finite, like a dice roll, which is 1 through 6. Or random variables can be countably infinite, like the number of packets arriving at a router in 1 hour, which can be 0, 1, 2, 3, and so on. Discrete random variables use a probability mass function, PMF. We write P of x equals P of x equals x. This is P of x equals P of x equals x. It gives the probability that x equals a specific value. On the other hand, continuous random variables take values in an interval. Think of temperature, time, or voltage. They use a probability density function, PDF. We write f of x in this shape. For a continuous random variable, p of x equals any specific number equals 0. You should pay attention to this important note. I repeat, for a continuous random variable, p of x equals any specific number equals 0. The density function does not give probabilities directly. Instead, p of l less than or equal to x, p of l less than or equal to x less than or equal to b equals the area under f of x from a to b. This case, you may ask, why is p of x equals 3.5 equal to 0? Because there are infinitely many possible values, the probability of any single point is too small to measure. We can only talk about intervals. Well, now we want to talk about expectation and variance. Two numbers summarize a random variable better than anything else. Its average and its spread. The expected value or mean is the probability weighted average, the expected value. For a discrete random variable, E of x equals the sum over all x of x times P of x. Also, the variance measures how spread out the values are. And this is the variance. The average is the balancing point of the distribution, and the variance can be interpreted as the spread of a random variable. We can calculate variance as var of x equals E of x minus mean quantity squared. This relation. Also, a useful shortcut for this relation can be var of x equals E of x squared minus E of x quantity squared, this part. Also, the standard deviation is just the square root of the variance. It puts the spread back in the original units. These have nice properties. E of ax plus b equals a times e of x plus b. Also, var of ax plus b equals a squared times var of x. Notice that adding b shifts everything but does not change the spread. Adding a constant value to a random variable does not change its spread or variance. Okay, if x and y are independent, e of xy equals e of x times e of y, and var of x plus y equals var of x plus var of y. We will use these properties all the time in proofs later. There are some common discrete distributions where you will see again and again. The first one is a Bernoulli with parameter p. One trial, two outcomes, success with probability p, failure with probability 1 minus p. For example, flip a coin or send one packet, it arrives or it drops. Mean equals p, mean of this random variable is p, and its variance equals p times 1 minus p. The second common discrete distribution is the binomial distribution. Binomial with parameters n and p, number of successes in n independent Bernoulli trials. For example, send 20 packets, count how many drop, p of x equals k equals n, choose k times p to the k times 1 minus p to the n minus k. Mean of this distribution is np, and its variance equals np times 1 minus p. The third common discrete distribution is Poisson distribution with parameter lambda. Models rare events in a fixed time or space. For example, packets arriving at a router, customers at a bank, or radioactive decays. P of x equals k equals e to the minus lambda times lambda to the k divided by k factorial. Mean of this random variable is lambda, and its variance is also lambda. The fourth common discrete random variable is geometric with parameter p, which is number of trials until the first success. For example, keep sending packets until one gets through. P of x equals k equals 1 minus p to the k minus 1 times p. Mean of this random variable is 1 over p. A useful fact is that when n is large and p is small, with np fixed, n and p fixed, the binomial looks like a Poisson. This is why Poisson is so common. Many real situations have lots of trials with tiny success probability. I repeat, when n is large and p is small, with np fixed, a binomial goes to Poisson distribution. Here is a networking example. A router drops packets independently with probability P equals 0.1. We send 20 packets. Let X equal the number of dropped packets. Then X follows a binomial distribution with N equals 20 and P equals 0.1. Question 1. What is the probability that at most 2 packets are dropped? We need P of X less than or equal to 2, which equals P of X equals 0 plus P of X equals 1 plus P of X equals 2. This part. P of X equals 0 equals 20. Choose 0 times 0.1 to the 0 times 0.9 to the 20. Which equals 0.1216. P of X equals 1 equals 20. Choose 1 times 0.1 to the 1 times 0.9 to the 19, which equals 0.2702. P of X equals 2 equals 20. Choose 2 times 0.1 squared times 0.9 to the 18, which equals 0.2852. This one, then we add them 0.1216 plus 0.2702 plus 0.2852 packets. 2 equals 0.6770. So there is about a 67.7% chance that at most 2 packets are dropped. Question 2, what is the expected number of dropped packets? According to the formula, we discussed about it in the previous slide. A of X is NP, which is 20 times 0.1, and this equals 2 packets. So on average, we expect 2 drops out of 20. For large N, summing these terms by hand is tedious. We usually use software or approximations. For continuous random variables, we need slightly different tools because single points have 0 probability. The cumulative distribution function, or CDF, is f of x equals p of x less than or equal to x. It tells us the probability that x is at or below x. The CDF always goes up or stays flat. It starts at 0 when x very negative and approaches 1 when x is very positive. The probability density function, or PDF, is the derivative of the CDF. F of x equals df over dx. The PDF must be non-negative and the total area under the curve must be 1. The probability that x falls between a and b is the integral from a to b of f of x dx, which equals f of b minus f of a, this part. This is the continuous version of summing probabilities. The expected value is the integral from minus infinity to plus infinity of x times f of x dx. Every formula from discrete probability has a continuous version. You can just replace sums with integrals. Here are the 3 continuous distributions you must know. 1, uniform distribution, or the interval a to b, constant density over the interval. F of x equals 1 over b minus a. Also, every subinterval of the same length have the same probability. Mean equals a plus b over 2.
this part. Variance equals b minus a quantity squared over 12. Using random number generation and as simple priors in Bayesian analysis, this distribution has applications. The second common distribution, normal or Gaussian with parameters mu and sigma squared. The famous bell curve. This is the famous bell curve, the normal distribution. F of x equals 1 over the square root of 2 pi sigma squared times e to the minus x minus mu quantity squared over 2 sigma squared. The Gaussian is central to the central limit theorem. Sums of many independent random variables tend to look Gaussian. And it appears everywhere in nature and engineering. The third common continuous random variable is exponential with parameter lambda. This distribution models waiting times f of x equals lambda e to the minus lambda x for x greater than or equal to 0. Mean of this distribution equals 1 over lambda. Variance equals 1 over lambda squared. This is the continuous version of the geometric distribution. Most importantly, the exponential has the memoryless property. P of x greater than s plus t given x greater than s equals p of x greater than t. If a component has already lasted s time units, its remaining life has the same distribution as a brand new component. In other words, it forgets its age. Okay, let us check the memoryless property with a real example. A server component has an exponential lifetime with mean 5 years. Since mean equals 1 over lambda, we have lambda equals 0.2 per year. The component has already lasted 3 years. What is the probability it lasts at least 2 more years? Okay, by the memoryless property, the answer is simply p of x greater than 2 because the past 3 years are forgotten. P of x greater than 2 equals e to the minus lambda times 2, which equals e to the minus 0.4, approximately 0.6703. This part. Okay, let us verify this directly to prove the property. By definition of conditional probability, p of x greater than 5 given x greater than 3 equals p of x greater than 5 and x greater than 3 divided by p of x greater than 3. If x greater than 5, then automatically x is greater than 3, so the top is just p of x greater than 5. P of x greater than 5 equals e to the minus lambda times 5, which equals e to the minus 1. P of x greater than 3 equals e to the minus lambda times 3, which equals e to the minus 0.6. The ratio is e to the minus 1 divided by e to the minus 0.6, which equals e to the minus 0.4. Same as before, this is remarkable. A 3-year-old component is exactly as good as a new one. This is why we use the exponential for simple failure models. In reality, most things do wear out eventually, but the exponential is a good first model. Now we move to multiple dimensions. The multivariate Gaussian is the most important distribution in statistical machine learning, computer vision, Kalman filtering, and Gaussian processes. A random vector X is d-dimensional space, is multivariate Gaussian, written n of mu and sigma. If its density has this form, f of x equals 2 pi to the minus d over 2 times the determinant of sigma to the minus 1/2 times the exponential of minus 1/2 times x minus mu transpose times sigma inverse times x minus mu, this part. Let us break this down. Mu is the mean vector. It is a list of d numbers. Sigma is the covariance matrix. It is d by d, symmetric and positive definite. It tells us how the variables vary together. The determinant of sigma scales the whole distribution. If the variables are very spread out, the determinant is large and the density is lower everywhere. The term in the exponential is a distance measure. It generalizes the z-score. Instead of dividing by variance, we multiply by the inverse covariance matrix, which accounts for correlations. The key property is if you start with a multivariate Gaussian and took at any subset of variables a marginal, it is also Gaussian. If you condition on some variables a conditional, it is also Gaussian. Gaussians are closed under marginalization and conditioning. This makes them incredibly convenient. In 2 dimensions, the covariance matrix has a simple form. X equals x1, x2 with mean mu1, mu2. Sigma equals this part, sigma 1 squared on the top left, sigma 2 squared on the bottom right, and rho times sigma 1 times sigma 2 on the off diagonals. Rho is the correlation coefficient. It is between -1 and 1. Rho controls the shape of the density. Contours, these are the contours. When rho equals 0, the off-diagonal entries are 0. The off-diagonal entries are 0. And the contours are ellipses aligned with axis. This figure, if sigma 1 equals sigma 2, the ellipse becomes a circle. For Gaussians, rho equals 0 means independence. This is special for most distributions. Zero correlation does not mean independence. As rho gets closer to 1 or -1, the ellipse becomes thinner and longer. These two figures, the variables become more dependent when rho approaches 1. The ellipse collapses to a line. The distributions becomes flat. The covariance matrix is no longer invertible. This happens in real data when two features are perfectly correlated. It causes problems for algorithms that need sigma inverse. When sigma equals sigma squared times the identity matrix, we have a round Gaussian. It looks the same in every direction, like a sphere or a circle. Okay, let us compute the conditional distribution. This comes up in Kalman filtering and Gaussian process regression. We have x equals x1, x2 distributed as n of mu sigma with mu equals 2 3 and sigma equals 4, 2 on the top row and 2, 3 on the bottom line. We observe x2 equals 5. We want to ask what is the distribution of x1 given this observation. For multivariate Gaussians, there is a closed form formula. The conditional mean is mu1 given 2 equals mu1 plus sigma 1 2 times sigma 2 2 inverse times x2 minus mu2. Plug in the numbers. Mu1 is 2, sigma 1 2 is 2, sigma 2 2 is 3, so its inverse is 1/3. And x2 minus mu2 is 5 minus 3, which is 2. Mu1 given 2 equals 2 plus 2 times 1/3 times 2, which equals 2 plus 4/3, which equals 10/3, approximately 3.33. This part. Before seeing x2, our best guess for x1 was 2. After learning x2 equals 5, which is above its average of 3, we raise our guess for x1 to 3.33. This makes sense because x1 and x2 are positively correlated. The conditional variance is sigma squared 1 given 2 equals sigma 1 1 minus sigma 1 2 times sigma 2 2 inverse times sigma 2 1, which equals 4 minus 2 times 1/3 times 2, which equals 4 minus 4 third, which equals 8/3, approximately 2.67. Our uncertainty dropped from 4 to 2.67. Knowing x2 reduced our uncertainty because the variables are correlated. So the answer is x1 given x2 equals 5 follows a normal distribution with mean 10/3 and variance 8/3. This is the answer. Okay, let us summarize what we learned in this session. 1. Probability rests on Kolmogorov's 3 simple rules. 2. Conditional probability updates beliefs. P of A given B is the fraction of B that is also A. 3. Total probability breaks hard problems into easier pieces. 4. Bayes' theorem flips conditioning. Posterior is proportional to likelihood times prior. We saw the surprising medical test example. 5. Random variables turn outcomes into numbers. Discrete uses probability mass functions. Continuous uses probability density functions. 6. Know your discrete distributions. Bernoulli, binomial, Poisson, geometric. 7. Know your continuous distributions, uniform, exponential, with its memoryless property, and especially the Gaussian. 8. The multivariate Gaussian, n of mu, sigma is described by its mean vector and covariance matrix. Its marginals and conditionals are also Gaussian. If you remember only 2 things, Bayes' theorem and the multivariate Gaussian support most of modern probabilistic machine learning. Here are 7 exercises. Please work through them before the next session. Exercise 1. Prove that if A and B are independent, then A and not B are also independent. Exercise 2. A bag has 3 red and 7 blue balls. 2 balls are drawn without replacement. Find the probability the second is red given the first is blue and the probability the second is red. Exercise 3. Emails are spam with probability 0.3. A spam filter catches spam with probability 0.95 but has a 5% false positive rate. If an email is flagged, what is the probability? It is actually spam. Exercise 4. X is Poisson with lambda equals 4. Compute P of X equals 2 and P of X greater than or equal to 1. For the second, use the complement. Exercise 5. Service time is exponential with mean 2 milliseconds. Find P of X greater than 3 milliseconds and the median service time. Exercise 6. Let X be normal with mean mu and variance sigma squared. Show that 0 equals X minus mu over sigma is a standard normal. 10. Compute P of mu minus 2 sigma less than X less than mu plus 2 sigma. You should get about 0.9544. Exercise 7. For a bivariate Gaussian distribution with rho equals 0.8, explain what happens to the density contours as rho approaches 1. Think about the ellipse becoming a line. I will post solutions on the course group. Try them first before looking at the answers. Okay, for further reading, the main textbook is Ross, Introduction to Probability Models, 10th edition. It covers everything we did today and more. For a statistics perspective, try Casella and Berger Statistical Inference. For connections to machine learning, try Dasgupta Probability for Statistics and Machine Learning. Next session, we move into statistical inference. We will cover maximum likelihood estimation, sufficient statistics, Bayesian estimation and conjugate priors, and an introduction to Markov chains. Please read the first 2 chapters of the mentioned books and also the course materials I sent to the group before next class, and do the exercises. Good luck.